or thank you, Mustafa. Yeah, and our goal is basically to bring experts like you guys together and discuss what are the new trends and technologies in the resilient energy cyber physical systems, and basically how we can integrate the artificial intelligence and IoT technology in the electric grid. So I think it's a good time to start. Let me start with the introduction of Dr. Fei Teng. Dr. Fei Teng is a lecturer in the Department of Electrical and Electronic Engineering in Imperial College, London. And he is director of the Energy Future Labs and also the deputy director of Xinhua and Imperial College Joint Center for Intelligent Power and Energy Systems. So he is working in this cyber physical area for many years, and his research is focused on efficient and resilient operation of the future energy system. And as it's very similar to the topic of his presentation today. So I don't want where we have an audience to wait more to hear your presentation today, Fei. So I just wanted to remind you, we are recording this presentation, and afterward it will be available on our YouTube channel and also in a HVL data science group, also in the task force webpage. Yeah, so Mushtaba, is there any other logistics to remind our audience?
No, you said everything. Thanks for your brief presentation.
Yeah, Fei, floor is yours, please.
Yeah, many thanks, Reza, and the task force invitation and organization. It's really a great pleasure to be here today to present some work we are doing at Imperial about cyber physical system resilience. I already see many familiar faces in the participants. So glad this opportunity, and also this is basically, I think this is one of the first seminars in the task force, which I also been part of with. So I hope this talk will give a good start of our activities in the general cyber physical resilience research elements. Okay, now let's just get back a bit more on kind of the topic today, where I actually have to confess that I also not have extensive experience on cyber physical system. My basic background is mainly on physical system optimization, scheduling, and a kind of power electronics penetrated power systems. But over the last few years, I have been fascinated about the difference when we extending the research scope from the physical based research into the cyber physical layer. So that's where I have been focusing my activity over the last few years. But again, I would like to look at the problem in a different angle, because for cyber physical cyber security research in most of current power grids, we are looking at the main research question is how we can make cyber system kind of reliable enough to support our physical system operation. However, today what I would like to share some of the thinking is, as we are looking at the cyber physical systems, is there anything in the physical layer actually we can use to improve the cybersecurity of the grids? The thinking originated, of course, from my own background about the physical system optimization. When you go along, you will see that the whole idea when we form this program. So yeah, I think that's the main topic I'm going to talk about, is a kind of, we call that proactive defense, moving target defense, by using the physical layer techniques to improve the cyber layer resilience. But again, I know we have many experts in audience about the cyber physical system, but I just will very quickly to introduce the general background. In the physical layer itself, we have seen great changes in the last decades, and we'll see burn more in the next decades to approaching the zero carbon targets of the world. So basically, we have traditional power system that has been there for for many time is basically we have all the controllability of energy in the generation, in the transmission level, and feed everything and controllability and the energy into the kind of, let's say, passive consumers. However, because of the development of smart grids technology, at the same time the distributed generation, we will see more and more reverse flow in the future, and also we desperately now need the flexibility, the controllability that actually in the lower level of the system. So in order to operate the system more efficiently and more cost effectively towards the zero carbon energy systems, we have to rely more and more on the cyber layer development. In particular, we have the sensors. I mean, in a simplified term, we have the sensors and the actuators as the interface between cyber physical layers. All the measurement and command will coming through different communication protocols. Depends on which layer of the system you're on, and this information will either feed into the OT system of generation, transmission, distribution, or if that at the household level, that's going to directly go to the home energy management systems. And in terms of the company level, all this OT network have been gradually merged with these IT systems for the cooperative networks. And all of these interfaces are now gradually again connected into the internet in order to either to get into access to the electricity market information, or in the distributed or home household level to provide services at a different layer. Those all critical developments as part of the digitalization for the future energy system. However, because of the increasing communication and also the data transformation, this also open up more attack surfaces for attackers, where they can exploit at a different layer of the cyber network to have to cause different consequences. There have been discussion about directly through internet to compromise either the OT networks or home management systems, or the attackers can even directly looking into the communication layers or the field sensors actuators. So basically speaking, in the future, the cyber physical system, there will be a risk both regarding the data in terms of environmental data and also the command. I would like a recent summary about what has been happening. So we think that is a problem in the academia, but is that really a problem in practice? Actually, some of this recent survey have demonstrated that we do see growing concerns, or actually reported, let's say, events that have caused different layer of impact by exploring the cyber vulnerability to the physical systems. In particular, the Ukraine one that has been talked a lot a few years ago, where more than 200,000 customers has been disconnected because the attacker compromised the OT system of the distribution operator and opened the breaker. Although, I mean, you can see that you may argue that's only a few hours, that's even less than what happened in the GB last year, 2 years ago for the blackout. However, in this particular Ukraine attack, the recovery from their SCADA system takes months. So they not only have immediate impact, they also have long-term impact. So yeah, those are only reported attacks. There are many more attacks that has been kind of carried out that is unknown. So I hope this put all us in line about the fact that we will there are and we'll see more cyber attacks in the future. We need seriously consider this problem. To speak of the investigation about kind of the reliability and the resilience, I think it's probably useful to clarify some of those definitions. This has been also extensive discussions in the physical layer, is where the difference between reliability and resilience, how the different metrics should be developed. So basically there is at least consensus now, I think, for reliability, we're looking at high frequency low impact events, while for resilience, that's low impact, low frequency, but once it happened, it will have devastating impact. So mapping that into the cyber physical system, I believe, it's my own opinion, if we are mainly looking at the cyber layer itself, I believe that in terms of the security, that can be also be classified in the reliability layer, where you have constant attacks or constant failures. The problem is we have to maintain the cyber layer into a certain level of reliability to supply or support the physical operation. However, if we want to really looking at what's the topic about cyber physical layer problems, where the cyber layer has been compromised to some extent and to start ready to have impact onto the physical layer, this kind of events is really rare. And also, but once it happens, it will have definite impact. So that I believe in terms of cybersecurity, for the cyber physical systems, the main research kind of matrix we are looking at, the probability resilience is the proper better one. Of course, we have the colleagues in has been developed this resilience framework over the last 6-7 years, and gradually people have, yeah, the society has been accepted for the resilience concept. We need to shift away from our kind of traditional thinking about preventive action dominate kind of reliability context. Yeah, for resilience, the main is to respond, get ready to respond and restore, right? If we are to use the same framework, looking into that, the cyber layer, are there any new challenges, or we just can easily adopt it? In my mind, there are two main elements we have to look at. One is the alert, because for cybersecurity, where most of the cases, the attack that's stealthy, right? There's no easy way to know there actually an attack happening. But if that's easily to be known, then that's not a problem, right? For most of really impactful attack, how we know there is a alert, how we can develop the alert so that we can respond, right? Another element is for the natural disasters. Normally when we develop it can be all developed by or described by a probability distributions. But here, when we discuss cybersecurity, there are people involved, right? So that's whatever actions you take, you have to think about your counterpart, your attacker from different will do, right? There will be most of that we have been formulated game theory programs or investigation. We have to model intelligence attack with the more random events of natural disaster that have to be kind of considered. So after giving the overview, I'm going to focus on the element about alert. That's most of my work has been focused on how we can detect the existence of attacks, cyber attacks, and in particular use some physical layer infrastructures and options. So one problem, I think this is probably one of the most widely investigated cybersecurity problem in the power system, which is the false state injection attack against state estimation. The reason that was investigated, apparently the major one is because that's the state estimation plays critical role in the system operation, and more actually in the future systems. That's the where we have their visibility of network. It is already very dangerous if we don't know what the system looks is like. It is actually become more dangerous if we know that in the wrong kind of in the wrong sense, right? So for state estimation system, normally I think it's quite maybe familiar with most of the audience, but just quickly, state estimation system is basically use all the SCADA systems, the environment data and the PMU data to estimate where the actual system states. The reason we use state estimation normally because we have noises, and also sometimes we have the faulty sensors, right? So for a very, however, all of this environment in fact are potentially be manipulated at a different stage of the data transformation, right? If we just give a quick example, for tradition, I mean, a simple is like say state estimator, least square estimator, where we can directly link about all the environment with the system by linearized environment functions. And one thing that we have for the state estimation is called by the detector, where we calculate the residuals to make sure the environment are correct, because we always have kind of noises and also some of faulty sensors. So because the existence of the bias detector, if there are random changes or of the environment, it's quite easily to be detected. However, in about 10 years ago, there is a paper, one of the first paper looking into the this particular injection problem, where if we assume we have an intelligent attacker instead of randomly inject or change the environment, if the attacker developed the attack vector according to certain rules, which based on the system topology, and in this case, the operator will have a wrong impression about what the system looks like, where the estimator will give is x plus c, which is different from the original system state, and make it more worrying is in this case, if you calculate residuals, there's no way the residual keep unchanged with the base case. So basically to say this, there's no way we can detect this kind of changes based on the bias detectors. Of course, we are researchers. Once we find there are problems, we try to solve it, right? So again, then we have to look at how we can detect this kind of attack. So the existing methods mainly are two categories. One is model-based. It's very similar as the bias detectors that I described, but there are more advanced versions of state estimation or both static and dynamic estimation has been used with the purpose of detect the existence of the data manipulations. Most of the case, we still use the residual test in a different form, and as this has been very familiar with system operator. However, one element here is the key element here is any model-based detectors, we have to rely on the assumption that the attacker do not know the model. Once this model has been known by the attacker, then there's no way in the general sense to have very reliable detections, right? One example that we did is try to say if attacker do not know system topology, as that's one of the mostly kind of assumed assumptions. Let's say they do not know, right? Even they don't know because of the new development of data machine learning techniques. Let's say it's actually quite easy to learn the topology. This assumption is the 16-bit system where we have been showing the attacker can access the data every 5 minutes. By using this topology, topology learning algorithms, we have demonstrated if the attacker want to design attack, it's only a few hours time to learn what's the topology like. So this is basically invalid the any model-based kind of detectors that purely rely on the system topology information. Of course, if you design more sophisticated model-based kind of detectors, this will make harder for the attacker to learn that topology. But most of the attacks, they stay even 6 months in the system, and eventually for any static kind of model-based methods for any static models, eventually the attacker will know that. Okay. However, the model-based methods have a good benefit, which is most of case they are quite reliable. If they work quite reliably, and also it's interpretable. It's very kind of well known by the operator how that works. That has been there for many years, very easily accessible. For the data-driven one, yeah, very quickly, I think many people have been familiar with this. Is basically you can either use the data-driven supervised learning or unsupervised learning methods where you learn some spatial temporal correlations of the system condition. It's not only the physical linkage, and also as most of the system are driven by the demand changes, the generation changes, there are kind of correlated. However, again, there are also problems. We need sufficient number of data to train the models, and also particularly if we have changing topology or changing drivers of system, it's very hard to train such a model. And another thing that I will also come back to mention again is the unavoidable false positives, because I believe for data-driven methods, most of we should use unsupervised because of the rare happiness of the attack, and it's really hard to anticipate the target or intention of the attacker. So for any unsupervised learning methods, there are always unavoidable false positives. And also at the same time, there's I just see a few works very recently to adversary attacks against any machine learning driven detectors. Fundamentally speaking, if we have the same amount of data that's collected by the attacker and defender, there's no way the defender can get a kind of ahead of the attacker if the data is only information they have to detect system, right? But I think more importantly, I would say the last one, the problem for data-driven detector is less familiar by the operator. It's not less interpretable. Imagine now even system operator do not have not accept data-driven operators. Now you want them to accept the data-driven detector. I think that's really quite long away to go. So all of this, both methods I mentioned we can classify them as passive detections, where you just wait there and to see whether either there are model changes or there are data alarm alarm of the data-driven methods. And I also mentioned that both of them have clear shortages. And then another thing that can be considered is basically whether we can get kind of one step ahead of attacker. We have actually proactively to do something to drive the detection, right? This is very similar as the idea about the shell games, where the operators will try to move the target so that to invalidate a technology so that the attacker will either target in the wrong place, or once that's attacked, it's very easy to be spotted. Yeah, because eventually I have been thinking what are the key advantages for the system operator. One thing is basically they have the ability to control topology, but attacker most of the case cannot, right? This is even they have, I mean, in the case in the future they have the same level of data of detectors and the defender and attackers, but the defender still have the opportunity to change the system topology as a system operator, right? So this is basically the idea that I'm trying to sell here is we should not stick into a static system. When we actively change the static system to dynamic systems to continue changing that will be really invalid all the information of the attacker has been collected, right? This is not new idea. I have to confess that this has been kind of first introduced in the IT networks, particularly you can change the IP address so that the attacker will target the wrong IP address to attack, right? But if we want to bring this idea into our power grids, so what are the key design principles, or what are the key considerations, right? So to start with, yeah, I have been mentioning the first thing we have to answer is why to move, right? I believe one of the fundamental advantages for the defender or operator, that say they are the same guy, is they can actively change something while attacker have to adapt, right? As long as you don't do that, then eventually there will be some point the attacker will penetrate you, okay? And then next question is, okay, you want to move, so what can be moved? In fact, again, it's also almost 10 years ago, people started thinking in the power grids, actually the topology can be changed. And gradually there are more and more device devices or transient switching for some part of operators that already be part of their operation options, right? So that by changing the device devices or switching, we actually not only sometimes optimize the power flows and the losses, they can also potentially invalidate the attack information so that any kind of attack based on their understanding will be spotted. The next question we have to answer is, okay, now we know what to move, but how to move it, right? There are different strategies. And the last one we also have to think about is when to move, if you can move it. The first two, I think most has been well covered and in the literature. Then I will probably focus a bit more on how to move and when to move. In terms of how to move, the most naive way, I think probably everyone, the first thing to get into mind, okay, as long as it's different, it should be fine, right? So we just random move we just random change some set point of the devices. As long as it's different from the previous one, the attacker should not be able to know. That's correct. But however, there are two problems I have to consider. One is the random move does not guarantee any performance. One extreme case is if you change the impedance proportionally together, it's equivalent to nothing has been changed. So change topology does not necessarily to change the attack surface, right? So that's we have to consider how we can guarantee certain performance. The next thing is your random change, there are also costs, right? As long as you are away from the optimal setting of devices, there will costs. Your random move, that will be a lot of cost potentially. So that's then the how to move question becomes what is the most effective way to really both effectively and optimally set the reactance values. So that's for effectiveness, we want to detect the attack with certain confidence. For the optimalities, we want to have its minimum impact on system operation. Either, most commonly used, again, minimize the cost increases because of change topology, or we also have some minimum perturbation and so on, but they're quite equivalently. So in terms of this question, actually, this again linked with my interest background, this is effectively a scheduling problem, right? Let's look at a defect optimization problem. That's already very well studied in the Power System Society for the physical system cost minimization, where we have the operation costs. This is OPF problem, where the delta X is the topology that we can change. And we want to minimize the total operation costs, where the power flows will be subject to any changes we make into the topology. And also we have all the constraints for generator and flow that have to be met. At the same time, the change that we can make for devices is limited. So that all this is the very classic defects optimization problem. And to make it more, then we have to add another kind of constraint or batch of constraints where we can guarantee certain performance of the detection, right? And then the problem comes into what is really a good effectiveness representation of the detections. Yeah, I will just first to introduce one of the mostly, I think, in the past 3-4 years, most widely used index, which they call that completeness of MTD, where basically the attack space is used to represent the MTD effectiveness. For example, if by changing, let's look at these 3 examples. If by changing the topology, the column space of each of the different measurement matrix still align together, this can happen if you proportionally change your system topology. In this way, there is basically no way to detect anything. This is all the attack will keep stealthy in the basic system. While you're gradually to try to separate the column space of these 2 measurement matrix before and after you change the topology, you will start to have more less and less attack space until to a certain point we have completely separated measurement space, the column space. So which is to say any attack will be directly detected. And some pioneer work in the last few years has kind of developed a analytical kind of constraint where we should require the rank of the original measurement matrix, and the new measurement matrix equals to the line of the 2 times of the line of the system of the lines. As long as this meets, this is basically any attack will be able to detect by BDD. Okay, it sounds great, but one thing I want to point out: this only work if there is no noise. Yeah, because any error in the residual, as long as it's that larger than 0, you can say there will be a something is wrong. But if we start to introduce the noises, which always have, and then this will not guarantee anything in terms of performance. I just gave you some of the examples when we change the topology. All of these 4 options actually have the same completeness. So basically the attack space are the same. But because when you change different magnitudes of the devices and you change that at different places, it effectively potentially have very different probability when we convert that into the by-day detection probability distributions. That will introduce quite different detection rate. Okay, so this is the reason on that is basically if we are getting into a noises, the actual detection will in fact is impacted by the attack strength and also affected by how much you change of the topology. Both of these cannot be considered if you don't consider noise, because anything larger than 0, you see there is attack. But if there's noise, you always have a threshold, and that threshold have been passed, so that we can raise the alarm for the attack. That's quick. Then we just introduced very recently. We introduced this idea we call that robust MTD, where we would like to explicitly consider the noise existence, and we want to implement the MTD to maximize the lowest detection rate for any attack with the same attack strength. And to basically, I think this is a bit too hard to. Basically, we're looking at a residual problem as this can be calculated, and we can define a lambda, which we call that as non-centralized parameter of the chi-square distribution. So the whole problem becomes we want to maximize or give certain level of lambda so that we can shift the distribution of the chi-square distribution so that we can give a certain level of certainty regarding the detection performance. The fundamental idea is basically we formulate a kind of attack defender game problem. We want to minimize the attacker would like to minimize the possibility of they are being attacked, while for defender, they want to maximize by changing topology, they want to maximize the probability of that being detected, right? We are luckily by looking at the inner problem, we have mathematically proved that actually this inner problem can be equivalent to be a problem where we only look at the smallest principal angle of two-column space between before and after change of your topology. So in this way, we can actually get rid of the minimization problem, directly replace that by this angle difference as the first layer of the solution. We change this max-min problem into a maximization problem where we want to maximize the smallest principal angle between two subspaces. And also we also did a bit analysis. We have proved that while sine theta we haven't get anything, actually we find out the cosine theta is actually the large singular value of the two-measurement multiplication of the two-measurement matrix. Sorry, the projection matrix, where we can really effectively convert this maximization problem into a minimization about this the columns, the optimization problem. What's this? Yeah, the distance of these two projection matrix is directly linked with the cosine theta problem. So that's this problem can be converted into this optimization problem. And then we did a bit of analysis to compare 3 different approaches where we can see that the robust moving target defense is significantly better than the random approach, in particular when we look at there is a small amount of attacks. When we have a very large amount of attacks, then they will be converged most of the case, because if the attacker strength is high enough, it's always going to drive the threshold. Another element that need to be considered is we call that the hiddenness of the MTD, because I mentioned one key assumption we have to make for cybersecurity is there will be intelligent attacks, right? So whatever you do for the defender, the attacker will think that's something to counter you. In this case, what is the hiddenness? Basically, we do not want to know we do not want the attacker to know we are changing our topology, or we do not want to know that there existence of the moving target defense. And also because of intelligent attack, whatever the tools available to operator is also available to the attacker. That's including both the BDD strategies and also moving targets, or also machine learning algorithms. So what's the consequence if the attacker knows there is a moving target existence, and then if the attacker knows that in the short term that they will stop attack? But that is good, but only for now. If they stop that, they can collect more data to analyze the moving target defense. They will know what, where, and how to change it. And in the end, they will develop something to counter the attack. And then how to hide, the next question, how we can hide from prevent the attacker knows that we actually implement moving target defense. This will be very much depends on the assumptions. So I'll give you 2 examples when we have the assumed attacker have different assumption on their ability. The one thing is we assume, if now let's just first assume the attacker have the same bad data detection mechanism as the of the operator. So basically, once they obtained the new environment, the attacker will do a state estimation by themselves first, right? Because they know the topology, and they can do a state estimation based on the new environment. So there are basically a chance that if you change the topology, which will mean that the new environment will not align with the existing topology, the old topology, and then the attacker residual will be alarmed, right? So the attacker will know actually this is not aligned, something is wrong for the environment. Then they know there is attack, there are change of topology or existence of MTD. So that's how we can do this. One key principle for the hiddenness of MTD is basically we should design the new environment which really lies in the column space of both original topology and the updated topology. Because in this way, the attacker, this new topology, this new environment will also bypass the attacker's bad data detector. There are some assumptions how we can to achieve this. But one fundamental assumption is basically we can assume, if we assume the load and generation will keep unchanged in a shorter period of time, some kind of original or some kind of pioneer work have proved that, in fact, this sufficient condition to hide MTD is basically to maintain the power flow unchanged. As long as the power flow is unchanged, this can be driven by different system states, right? As long as the power flow is unchanged, the attacker will not able to detect there is a change of topology. However, one thing we have to be thinking is for hiddenness of MTD, which you want to design a environment which belong to the joint column space of H and the change topology. However, if you want to increase your effectiveness of MTD, we call that if you look at the complete MTD, you want to these 2 space to be 0, right? Because you do not want a environment which can belong both spaces, which means you cannot detect. So this is the basic confliction between the hiddenness and completeness in the MTD. You should see in this kind of front, because this hiddenness and completeness, you cannot really compromise between them. They are conflicting each other in the case that there is no noise. One research that we did a bit similar as the borrowed robustness concept is basically we are looking at actually there exist noises that is bad. The noise existing of bad for the detection or for the effectiveness of MTD, but actually because of existing of the noises, this is actually beneficial to hide the existence of MTD. In particular, one element is the attacker will very hardly to know actually the noise assumptions, while the defender has much clear noises. So this is to say that we do not, because of existence of noise, we do not really need it exactly. We only need to maximize the kind of distance between these two column space, and then that actually can support the hardness of MTD. It's a reversed problem for the operator where they want to kind of minimize the largest angle. This is kind of how to say that is the mapping between the robust MTD into the completeness, into the hardness of MTD. You can have more details in this paper. I'm running out of time. Yeah, another element we did is about if we assume the attacker have the learning capabilities, then they can easily to learn. There are different topologies. Even they don't know the topology. This example we have done is basically if you generate the scenarios about environment based on different topology, and then if you use clustering algorithms, if the attacker have access to the clustering algorithms for the different topology, that drives the kind of the environment, it's very easy to really cluster different environment into groups. In this way, we can really clearly identify each of these group which as corresponding to one particular environment topology, and then we can use that information to design the attacks focus on one topology, right? So in this way, we have a paper to really illustrate this new type of unsupervised learning based attack. So this is to say, because of the existing of such kind of detection or counter mechanisms, we have to redefine the way that we implement our moving target defense. So what we assume here is basically in order to not to be spotted by the clustering algorithms, we have to reduce the changes, because large changes is very easy to be spotted by the attacker in terms of topology changes. And also we should change from discrete changes into continuous random changes. So this brings into this new idea, we call that watermarking, where we inject changes into the devices and make it looks like the noises. But the only thing different in this way, the different noises, the operator will know exactly the number, right? But from the defender perspective, from the attacker perspective, when they do the measurement, it seems just a measurement noise. In this way, the attacker will not be able to separate any different topologies. But we still have a problem here, because as we are significantly reducing the magnitude of changes, it's really hard to instantaneously spot any attacks, because the attacks is proportionally to the changes of your make and also the attack vectors. But if we changing the traditional way from kind of marrying one residual to the marrying cumulative summit residuals, we call that cumulative summit monitoring, which actually we can still see that there are attacks that happened, right? Even though individually we can now see significant drive of the threshold, but if you have cumulative errors, that will be easily to be alarmed, to be kind of drived. The key design consideration here is how we can really balance the maximum size of watermarking and the number of how long you want to spot the attack. Here is basically if you have larger volume of watermarks, you will need less cumulative errors to confidently drive the alarm. But in that case, there will be a higher risk to be spotted. Yes, now we have discussed how to move. There are mainly three elements. It's basically we have to balance the effectiveness, robustness, and cost when we do move. And we also want to hide this existence of the move so that attackers to be more confidently implement this kind of strategy. The next thing I will just very briefly go through is the when to move, because one key element, I think the limitations from moving target defense is if you continuous move, that will be 100% secure in most of case, but there will be a lot of costs. If you move every 5 minutes, there are some estimation you will have increased 2-3% of of the costs, which is really hardly acceptable for a system operator, right? Because for such rare events, no one will pay 2-3% of the costs to prevent it. So the key element is here how we can properly design when to move to reduce the costs. But that's already, of course, the cost element is a big part when we consider how to move, but also when to move is a bigger question here to be answered. Again, we look at why we need to consider this question, because there will be cost and effective kind of balance. And also, if you continuously utilize the moving target defense, that will be easier for the attacker to know that the existence of that and counter that. So what are the options we have? One thing is traditionally we can do periodic changes of the reactants every 5-10 minutes, or sufficient small kind of interval before the attacker will learn the actual topology. But how often is the question, right? Some of the work, some of the college has analytically solved that to say actually for a few hours time is very likely, even from few hours time, we will allow the attacker to learn the topology. So in this way, if you want to go to a periodic, you have to change the topology every few hours. Okay. The same story is verified by our more kind of data-driven or machine learning based algorithms. However, we have another options, which is we call that event trigger, right? You do not periodically change your topology, but only change that when actually there are some indicators where there may be something wrong, or do a combination of periodic and event trigger to complement each other. But then the problem comes, what is the best trigger we should use, right? It's very, yeah, sorry, I'm running out of time. Let's quickly. So in here, I want to bring a little bit of discussion before we go back to the triggers is about the data-driven detectors, right? You have, there are significant work in there, unsupervised learning and supervised learning approaches. We also did a little bit of work in this element, which has been demonstrated quite good by taking into account the spatial temporal correlations, not the physical correlations, but the correlations of the load and the generation, so that this information can be used to drive attackers attack. I don't have time, but I want to mention here is for any, I mentioned that already, for any data-driven detectors, there are always a problem about false positives, particularly when we use unsupervised learning approaches. There you have to compromise. If you want to control your false positives, you have to compromise your positives for most of the, you may be able to improve certain balance, but eventually you always have this kind of trade-off. So now if we put really together the data-driven detectors and MT detectors side by side, right? For data-driven detectors, the problem is the balance that have to be achieved between false positive and true positives, right? Basically to say we are really scared about false positive, because for IT system, you don't care, is because if you have false positive, you lock someone off, ask him to rejoin the network, then that's it. But for the power system operators, if you continuously say, okay, this may be wrong, this may be attack, okay, that would not be acceptable. For the moving target defense programs, this will basically rely the same as a bad detector, the system operator like it. However, you cannot continually use that, right? And if you use that, there will be a costs. So that if we really bring these two elements together, so why not bring them together? So the data-driven detector actually can be used as a trigger to move the MTD. So, okay, let's say we suspect there's something wrong. Instead of raising alarm directly, we can trigger MTD. Well, now MTD will be able to verify whether this is actually a true attack or it's just a false positive. By using this combination, we will significantly, on one hand, reduce the false positive of data-driven detector, on the other hand, reduce the utilization of MTD. So basically, this is one of the examples we have done. If you have some measurements and get into the system, well, this measurement will bypass the conventional by the detector BDD but let's say some data-driven detectors thought, okay, there may be something wrong, okay? And if the data-driven detecting is fine, then that's okay. There's no actions taken. But in this way, if we think something is wrong because the data-driven detector have a threshold that risk, and then we can use some as a trigger, and also not only will trigger MTD, we'll also tell MTD which part might be wrong. Okay, that will be used to design MTD by changing topology, and in the next round of the measurement, we will have new measurements, and then we can use BDD to see whether actually there is a change of the measurement has been changed, because now the attacker do not know the new topology, right? In this way, if we think if this measurement still meet the threshold, which means actually there's no attack, the deep-driven detector is just a false alarm. And however, on the other hand, if now the bad data detector under the new topology has been triggered, and then we can raise alarm on that purpose, on that kind of basis. So these are two different assumptions. Whether if it's continue as no attacker, we can continue. There's no kind of raise of alarm. While if there is a different kind of attacker that really actually exists, then we can clearly see there's a driver detection. So yeah, just quickly to say that we have been demonstrating the benefit of this. If you use purely data-driven detectors, basically when you have different, if you want to have lower false positive rates, you have to reduce the detection rate. By combining these two approaches, now we can maintain the false positive rate as the 1%, and while at the same time we can no, not as 99.5%, but at the same time we can maintain the very high detection rate. Okay. In this way, we can also look at the triggering period. If you do periodic, assuming every 15 minutes you do a state estimation, that needs one day you need 96 times. But if you do event trigger, because this is basically only false alarm, basically the only false positive happens, because most of the case there is no attack, right? If there is a false positive, you trigger AMTD, which is about 3-4 times a day. While we can maintain the same false positive, while very clearly this is the new false positive by combining these two methods together, while we can maintain one of this very high detection rate. Apologies, I think that's take a bit more than I have been expected. So today I just want to mainly introduce this moving target defense. Some of the work are still ongoing, so it's mainly to look at the problem is why to move, and it's basically because of intelligent attackers. The static topology will not work eventually for the bad data model-based detections, and also for data-driven approaches, we always have these false positives that's not acceptable. And the next question is about what to move. That has been studied. You can either do device or transmit switching, and how to move. The normal consideration is effectiveness, robustness, and costs. And also, if you
sorry,
want
Fei, I interrupt you. So, can you wrap up maybe in 1
minute?
minute?
We're finishing now. So then we have discussed when to move is either periodic or event trigger. I think that's all. Apologies that take a bit longer than I thought. Yes.
Very good. Wonderful. So yeah, any question from audience? Yeah, feel free to use the chat or even open your microphone and ask it by yourself. Oh yeah, please go ahead.
Thank you so much for your presentation. I have just a couple of questions. I'll stick to one.
Please. Mm-hmm.
So the very first question is that robust MTD.
Yeah.
So what's the computational cost for the largest network? Because if you're thinking about robust MTD in real time, and as I understand that system operator, they may have like 4 or 5 seconds when the system state changes and they do all the control actions, right? In that case, the robust MTD for a very large test network or very large power system should be fast enough, right?
Yeah, you mean the optimization problem or the effectiveness? Because this problem is the same as the.
I mean the detecting problem itself, right?
That's very fast. We have, I don't know exactly the figures. We have developed the convex optimization for that particular constraints. Basic is here. This constraint, we have developed a convex optimization program. So that is actually convex. Okay. And then we can
another question is about learning about the topology.
Yeah. Yeah, yes, please. What do you, the question about the learning one? It's right over here. Of 2 places we have learnings. Yeah.
So my understanding is that the topology, I mean, it's like an NP-hard problem. If you look at the connected graph, there can be it can be exponentially higher. I mean, you have many combinations, right?
Yeah.
The topology, you can have lines turns off, maybe, or some points
Exactly.
where the loads generation turns off. But then we're learning all that for such a NP-hard problem. Isn't that costly?
That's a good question. If you really start from blind, it's true. Yeah, if you just treat the environment as data, you learn from that, is true. But this is a collaboration we had with Tsinghua University. They actually developed this two-layer kind of identification program, where in the first layer we use the knowledge we have for this power system. We have this physical laws. Basically, you can also argue this maybe somehow physical informed information. You are not start from scratch. You want to blend your kind of physical information into the learning program. And in the first layer, you can identify the connections. The core, I mean, the most hard part is identify the connections, right? But we know that there are some physical information that could be used. So the whole process is that. But also, I want to say that the colleagues in Warwick have done that analytically. I mean, it's also analytical. So if you want to learn this, it depends on the algorithms. It's the same conclusion. You can use few hundreds or thousand data. You can learn properly your topology from there. But also on the other hand, this part is basically most of the work is not developed for the attacker, but there are a lot of works for the guys in distribution network. They want to learn the topology based on data. That can be directly borrowed by attacker to use that.
Right.
It has been a lot of development in the past few years. Yeah.
All right. Thank you so much.
Thank you.
Very good. So any other quick question? Yeah. Very interesting. And yeah, Mushtaba, do you have any question or comments?
No, I think yeah, the time is running out and we should finish it in 1 hour.
Apologies for that.
Yeah, that was very, very interesting, very informative, and thank you for joining us today. I would like to thank everybody, and please follow our upcoming events and bear with us. So hopefully we will have more in this area for to bring to your attention. Yeah. So I think, Mushtaba, we can stop the meeting here. Thank you, everybody.